We are, all of us, star stuff. What the heck does that mean? Well, today, it means you get a science lesson. I'm going to start with explaining fusion about as simply as I can. This is a proton and an electron. Together, they form a hydrogen atom. There's one thing that most types of atoms have that a hydrogen atom is missing, a neutron. During the fusion process, a proton from another hydrogen atom comes in and fuses to the first, but in the process, it loses its charge by emitting a positron and becoming a neutron. That positron immediately annihilates on one of the extra electrons in the system and produces two gamma-ray photons. It also emits a chargeless neutrino, and we'll come back to those later. After that, we're left with one proton, one neutron, and one electron. Whenever an atom has an irregular number of neutrons, which this hydrogen atom has, it's called an isotope. This is an isotope of hydrogen we call deuterium. But we're not done yet. We haven't even gotten to another element yet. Our deuterium atom is trucking along when it runs into another hydrogen atom. This time, the proton comes aboard, and we've got two protons, two electrons, one neutron, and one emitted gamma-ray photon. Under normal circumstances, a helium atom has two neutrons. So this is another isotope, this time of helium. Now don't worry, we're almost done. Another helium isotope formed under the exact same circumstances comes along and fuses with the first. It ejects two distinct sets of protons and electrons in the form of hydrogen atoms, leaving two protons, two electrons, and two neutrons. And with that, we've got our first full new element. The majority of the sun's energy comes from the emitted gamma-ray photons, or the motion of the protons in the process. But all of the hydrogen will one day be used up in the sun, leaving nothing but helium. Now, our sun isn't large enough to supernova, so instead it'll blow into what's called a red giant. The outer shell will expand while the core contracts, and the helium will finally be heated up enough in that contraction to itself begin to fuse into carbon in another, even more complicated process. Now, after that, there just isn't enough mass in the sun to form many more elements. After only a few million years, the helium will run out. The sun will collapse into a white dwarf, radiating away heat left over from its 10 billion year lifespan until there's nothing left but a black dwarf center. But there are heavier elements than carbon out there, so where did they come from? Well, our sun is small on the scale of stars. After a star gets to be about 8 times the mass of the sun and comes to the end of its life, things start to get a little bit more interesting. You see, while our star is too small to compress carbon down to fuse, these larger stars have no problem. In fact, in the case of some of the particularly massive stars, carbon is part of the normal fusion process during life. Carbon, though, isn't exactly an efficient fusion fuel. The issue comes from our friend the neutrino. I told you we'd get back to that. The complexity of these processes, which prevents me from explaining them to you in any meaningful way in this short video, are also what eventually leads to the quick death of these stars. Because the processes involve so many steps, and a majority of fusion steps involve the creation of some neutrinos, a lot more of them are created in these complex processes. Neutrinos are chargeless and almost impossible to stop because they don't bump into things. Our sun loses some of these on a regular basis. Every lost neutrino is mass it can never get back. With larger stars, the neutrino emissions begin to ramp up significantly, especially towards the end of their lives. When the energy created isn't enough to keep going, the star compresses further, heats up more, and begins fusing heavier and heavier elements. Carbon becomes neon, neon becomes oxygen, oxygen becomes silicon, silicon becomes iron, and iron, well, that's when a star dies. Fusion of iron is possible, but it actually takes more energy to fuse iron than you get from fusing it. A star with an iron core has no viable fuel left, and its giant mass will immediately begin to collapse. However, there's a tremendous amount of energy in the compression of the collapse, so the iron does fuse. The iron in the core acts like an impassable barrier. Now, there are many ways for a star to die from here, depending on the mass of the star and its density. Some will form neutron stars, some will form black holes, and some will rip themselves apart in the explosion. But all elements heavier than iron, almost everything in this part of the periodic table, is formed as part of the byproducts of the star's life and death, either in the core or in the shock wave after the collapsing shell smacks into the core, bounces off, and heads out into the cosmos. The elements that make up our bodies were formed in the nuclear fires at the center of stars long dead. We are all of us star stuff. Thanks for watching. If you like it, don't forget to subscribe, like the video, and tell your friends. Thanks.